Welcome to video 4. We have a working multi-layer perceptron. But so far we just trusted it to train. Today we open the hood. We'll look at the activations flowing forward and the gradients flowing backward. And see why getting these healthy is the difference between a network that learns and one that's stuck. Then we'll meet batch normalization, one of the most important tricks in deep learning. We'll answer 4 questions. Why is the loss enormous at the very first step? Why do tanh neurons sometimes die and stop learning? How should we actually initialize the weights? And how does batch normalization make all of this robust? Chapter 1. A puzzle. The very first loss is far too high. At the very start, before any training, the network knows nothing, so it should assign roughly equal probability to all 27 characters. That gives an expected loss of minus log 1 over 27. About 3.3, but in practice we often see a loss of 27 at step 0. The network isn't unsure, it's confidently wrong. The result is a telltale hockey stick loss curve. The first several iterations are wasted, doing nothing but squashing those overconfident initial predictions back down. We can fix that, and get free improvement, by initializing better. Chapter 2. The fix. Start with tiny logits. The logits are the final scores. And they're large only because the last weight matrix is large. So we shrink it, multiply W2 by a small number like 0.01. And set the final bias to exactly 0. Now the logits start near 0. The softmax is nearly uniform. And the loss begins right around the expected 3.3. We don't set the weights to exactly 0. Though, because a little asymmetry helps the neurons learn different things. Chapter 3. A deeper problem. The tanh is saturated. Now the harder problem. The hidden layer. Remember, tanh is S-shaped. Steep in the middle, but flat at both ends. Those flat tails are where it saturates, outputting almost exactly -1 or +1. If the inputs to tanh are too spread out, which happens when W1 is too large, almost every neuron lands in those flat tails. A histogram of the tanh outputs shows everything jammed against -1 and +1. Hardly anything is in the useful middle region. Chapter 4. Why saturation is fatal. Dead neurons. Why does that matter? Look at the gradient of tanh. 1 minus tanh squared. In the active middle region, tanh is near 0, so the gradient is near 1. And learning signal flows through. But out on the flat tail, tanh is near 1, so the gradient is 1 minus 1. 0. No gradient reaches the weights behind that neuron. It is effectively dead. If a neuron is saturated for every example in the batch, it never gets a gradient and never updates. These white cells are exactly those dead neurons. A network full of them is wasting most of its capacity. Chapter 5. Bringing the neurons back to life. The fix mirrors what we did for the logits. Make W1 smaller too. With smaller weights, the pre-activations are no longer extreme. So the tanh outputs spread out nicely through the active middle. On the left, the saturated histogram before. On the right, a healthy bell-shaped spread after. The dead neurons come back to life. And training speeds up. Chapter 6. The principled answer. Preserve the variance. So how much should we scale? There's a principled answer. When we multiply by a weight matrix, each output sums over fan-in inputs. And that multiplies the variance by fan-in. if we don't want the signal to blow up or vanish as it passes through layers. We want the output variance to equal the input variance. Working that out, the weights should have a standard deviation of 1 over the square root of fan-in. Bigger layers get smaller initial weights. Chapter 7. Kimming init and the gain. There's one more wrinkle. A nonlinearity like tanh squashes the signal, shrinking its variance. To compensate, we multiply by a gain. This is the kimming, or initialization. Standard deviation equals gain over square root of fan-in. For tanh the gain is 5/3. For a ReLU it's the square root of 2. Modern frameworks do this for you. But it's vital to understand why it exists. To keep activations roughly unit Gaussian all the way through the network. Chapter 8. Why we need something more robust. Careful initialization works, but it's fragile. For one layer you can tune it by hand. For a deep network with dozens of layers, keeping every single one perfectly scaled is hopeless. Tiny errors compound, and the activations slowly drift until they explode or vanish. What we really want is for training to be robust. To not depend so delicately on getting the init exactly right. That is the motivation for batch normalization. Chapter 9. The idea behind batch normalization. The insight is almost cheeky. We spent all this effort trying to make the pre-activations roughly unit Gaussian. So why not just force them to be unit Gaussian directly? Batch normalization does exactly that. It takes the hidden pre-activations and normalizes them. Every single batch, whatever messy distribution the pre-activations have, we recenter and rescale them into a clean, unit Gaussian shape, right before they hit the tanh. Chapter 10. The formula, and the learnable scale and shift. Here's the whole operation. We compute the mean and standard deviation of the pre-activations across the batch. We subtract the mean and divide by the standard deviation, giving a unit Gaussian, but forcing exactly unit Gaussian everywhere would be too rigid. So we add two learnable parameters, a gain, gamma, and a bias, beta. The network can scale and shift the distribution however it likes. At initialization gamma is 1 and beta is 0. So it starts perfectly normalized. But it's free to move away from that during training. Chapter 11. A strange side effect that turns out useful. Batch normalization has a weird consequence. Because the mean and standard deviation are computed over the whole batch. A given example's output now depends on the other examples it happens to be grouped with. Mathematically that's a bit horrifying. Examples are no longer processed independently. But in practice it helps. The small batch-to-batch jitter acts like data augmentation. A gentle regularizer that makes the network generalize a little better. For years people kept using it partly because it was so hard to remove. Chapter 12. What about a single example at test time? There's a catch at test time. If we want to evaluate a single name, there is no batch to compute a mean and standard deviation from. The solution is to keep a running estimate during training. At every step we nudge a running mean and running standard deviation toward the current batch's values. With a tiny momentum, these need no gradients. Then at inference we just use those fixed, remembered statistics, so the network behaves deterministically on a single input. Chapter 13. A small but tidy consequence. One neat detail. When batch norm subtracts the batch mean, Any bias you added in the previous linear layer just gets subtracted right back out. So that bias becomes completely useless. It has no effect on anything. In a batch-normed layer we simply remove it. Batch-norm's own beta parameter plays the role of the bias instead. Chapter 14. The diagnostics that tell you it's healthy. How do you know your network is healthy? You measure its vital signs. Look at the forward activations. They shouldn't all be zero, nor all saturated at the extremes. Look at the backward gradients. They should be a similar scale across every layer, neither vanishing nor exploding as they go deeper. And look at the ratio of each update to the size of the weights it's changing. A healthy value is around 1 in 1,000 per step. Much larger and you're training too fast. Much smaller and you're barely moving. These plots are how practitioners debug training. Chapter 15. The Big Lessons. To recap, initialize the last layer small so the very first loss is sensible. Scale the weights so activations stay in the active region, not saturated. The principled rule is skimming initialization. Gain over square root of fan in. And batch normalization normalizes the activations for you, making training far more robust to all of these choices. Above all, always look at the statistics of your activations and gradients. A network you can measure is a network you can fix. Next time, we go back to backpropagation and compute every gradient by hand, to truly understand what the autograd engine is doing for us. See you there.